In this video, we're going to do another example problem that's just illustrating how we use approximations of trigonometric functions in real-life situations to solve problems. So we're going to see in this example that there's a circumstance where we just have an angle, and it's not necessarily a special angle like 30, 60, or 45, or it doesn't even necessarily have a reference angle that's a special angle. And to solve the problem, we need to evaluate a trig function of that angle with no other context. That's it. We're just given the angle. And so to do that, if it's not a special angle, we have to use an approximation, where the general definition of trig functions, that definition is used to do a numerical approximation of the trig function value. That's the only way to evaluate trig functions of angles like this. And this is done, these numerical approximations are programmed into calculators. And so we use a calculator to evaluate these trig function values. So, okay. Any offset between a stationary radar gun and a moving target creates a cosine effect that reduces the radar reading by the cosine of the angle between the gun and the vehicle. That is, the radar speed reading is the product of the actual speed and the cosine of the angle. Okay, so we want to find the radar readings to the nearest unit for auto A and auto B. What they're saying is that you have a radar gun here, and there's what's called a cosine effect, and that the reading is that the radar gun shows is a little bit less than the actual speed of the vehicle because of this cosine effect. And the radar gun reading, they said you can calculate it by multiplying the actual speed of the vehicle by the cosine of this angle between the line of action of the radar gun and the line of the vehicle. So the radar gun reading, we'll say, is R sub auto A would be the actual speed of the vehicle, 70 miles per hour, times, they're saying the cosine of this angle between the line of action of the radar gun and the line of the vehicle, the line of motion of the vehicle. So cosine times cosine of 10 degrees. And so we know that any trig function is going to be, you get a trig function value that's going to be unitless. It always will be, because it's a ratio of not necessarily two lengths of the side of a triangle, but it's a ratio of depending on the units of which you're. In this case, it would be, you could think about it like these would be two speeds. You have this speed, and then here's the speed that the radar gun's picking up. The amount that the car is changing, the speed at which the car's position is changing with respect to this direction is this actual speed of the car, but the speed at which the car's position is changing with respect to this direction is a little bit less, and that's what the radar gun's reading. And so but that's a ratio of two speeds, and so that's unitless. And so we have miles per hour times something unitless, we're going to get miles per hour, which is what we expect. That's the radar gun reading of the velocity. So now you can see, though, to get this, to evaluate this, you can think about the software inside of the radar gun. Well, I don't even know if the software is calculating this. Maybe if it does an autocorrect, I don't know if it autocorrects itself or what, but to do this calculation, we need to just from scratch evaluate what is cosine of 10 degrees. So we need to do an approximation. It's not a special angle. We need to do an approximation for this. So we come to the calculator. Cosine, make sure we're in degree mode. Okay, it gives an exact answer, but it can't simplify it anymore, so it's just cosine of 10. That's the exact answer. So we need an approximation, so we do control, and you see this approximate symbol, and there we go. Now we'll just use all of the digits and multiply that times 70. Okay, now there you go. There's the radar reading, and so to the nearest unit of speed, so we want to round this digit, so 69 miles per hour. That's the radar gun reading of vehicle A. Now, the radar gun reading of vehicle B is So it's moving at 70 miles per hour, but that angle is going to be a little bit bigger, right? Because the car is closer to the cop car. So it's cosine of 20 degrees. So you've got cosine of 20 times 70. Okay, so 60 round to the digit, that's 66 miles per hour. Now, you would think that the radar gun would like be able to auto-correct itself for this, but I'm not sure how that works. But yeah, so in the next question, though, they ask, can we look at this diagram and explain why this happens? And so this would give some explanation about maybe if the radar gun potentially can't autocorrect itself. I mean, I don't know. But it's reduced by the cosine of the angle theta shown in the figure, where r represents the reduced speed and a represents the actual speed. Use the figure to show why this cosine effect occurs. So yeah, it's like the radar gun is, you can imagine, I guess it's like it sends out a laser, right? And it's measuring how fast that laser is, like, you know, the distance between the laser and the gun is decreasing. Maybe that's how it determines the speed. Well, that's going to be, it's the rate of change of this line, not this line, which is, you want the rate of change of this line with respect to the car, not this line. And so that's the issue. The rate of change of this line with respect to the cop car and the car is different than this line. So, and this is going to be the radar gun reading. And so I don't know, maybe there's no way. I mean, how could the radar gun know of this, calculate this angle theta? Maybe it can't. So what does that mean? Are the police officers kind of guessing the speed? You know, because they need to round up the speed a little bit based on this angle. So are they giving people tickets by you know, assuming that they're going 3 or 4 miles an hour faster than their radar gun showed? So you could argue that in court maybe. But yeah, that's the idea.